Welcome to How to Supercharge Your Team's Productivity with MLOps. I'm Moses Goodman from ClearMap. I'll tell you a bit about ClearMap, how we created this platform, what you can do with it, and basically how to be more efficient with the help of the ClearMap open source platform. Let's get started. So a bit about myself and the company. I'm Moses, founder and CTO. We were previously called Allegro AI, just recently rebranded as ClearML. I have 15 years of experience in machine learning and deep learning, from the early days of kernel methods and SVMs up until last and greatest in deep learning, transformers are everything, etc. I'm a professional PhD failure, which means that I never actually graduated. To the dismay of my mother, I went and started a company. And we started this company actually to solve all the issues that we had as deep learning and data science practitioners. Trying to solve the greatest challenge of creating a continuously learning platform or workflow. And the main challenges were and are always how to take code and be able and create something that will allow you to reuse the code itself without constantly writing infrastructure code and instead concentrating on the data science. And this challenge led us to build the ClearMap open source platform. And today I'll explain how to take that platform and how to integrate with your code with very little effort. When we started this journey, one of the goals of ClearMap was always to be able to very quickly integrate into your workflow itself. So I don't need to spend a lot of time taking my code and integrating with the automation platform so later I can reuse and automate these processes. And today I'll try to explain how that is actually done and kind of behind the scenes and how everything is working. Okay, so why exactly is it's such a huge challenge to create this CI/CD approach of continuously integrating and deploying when it comes to machine learning? And I guess the biggest issue is always that traditionally software development is quite a linear process, right? You write some code and you have your Jira tickets and you have your bugs and your fixes and everything kind of progresses in a linear way. What I have today is definitely better than what I had like 6 months ago. But when it comes to machine learning and deep learning, it's a bit more challenging. And when I say it's a bit more challenging, it actually involves the code itself, the parameters or configuration and whatnot, and the data. And the data is constantly changing, and the code we constantly develop, and the parameters we need to kind of find the best set of parameters in order to get everything to work. Not only that, the process of actually verifying that something is working is very long. So in traditional machine learning, that can be several hours, but if we think about deep learning, that could be several days even. And these long compilation, if you like, sessions are quite challenging when we're trying to first see if our code actually works and then later find what's the best set of parameters in order to actually say, okay, the model that these parameters produce is the currently best model that can be achieved, and we need some more data in order to kind of create the next step in terms of the evolution of the model. Okay, so what exactly these challenges amount to? They amount to being able to take our code and the data and the configuration. You can think of this as the 3 pillars of MLOps. Making sure that we can reproduce the code data and the configuration, and making sure that we can automate the process of reproducing this set of parameters on a remote machine. Then obviously the extension of that, I want to be able to change the data and change the parameters without changing the code. So essentially, we can think of this entire process of abstracting the data and the configuration from the code. And that is always easier said than done, because creating an abstraction is quite challenging. And as I mentioned before, we have to make sure that we are not spending too much time on the software infrastructure, but on the data science itself. So it means that someone else needs to do that very heavy lifting for us in order for us to actually have that abstraction as part of the process itself. And then the last one is obviously, so I mentioned before, these long computation sessions, these long training sessions. Someone needs to take care of allocating resources. So whether these are machines on the cloud, these with strong CPUs, or GPU instances on the cloud or on-prem, someone has to allocate them and then send the job itself, the training session, to those machines. And that's always a challenge because those jobs, they need to be self-contained, right? So those jobs need to have everything that they need in order to train them, the model itself. And as we mentioned before, we have to have the code there, the data, and obviously all the environment and the parameters. Okay, so what exactly are MLOps in terms of kind of how people think about MLOps? So I'll start with the last one. It's actually model serving, right? At the end, we have to have a model that we can serve or use in inference mode. And that's our goal at the end, to have that model, to be able to use that model in order to predict something or classify something or find something in an image, etc. Then we have the data pre-processing, which think of it as kind of taking the data from production systems that we usually don't have direct access to as developers, taking that data, bringing it into the R&D, using that data, and then obviously training a model. And then obviously the third one is the hardware abstraction. As we mentioned before, how do I orchestrate a job? How do I send it for execution? How do I train a model in a way that will enable me to automate these processes, right? How do I, either from code or from some sort of a UI, send another model to be trained on new data? That's basically hardware abstraction, because I have the ability to say, I need a specific type of machine to run that code. And then obviously everything around it that enables this entire thing to work. But from an R&D perspective, this is something that is a bit different, right? From an R&D perspective, MLOps is actually being able to create visibility into your process of creating a model or training a model, right? So think of it as kind of the goal of provenance, right? The understanding that I need to be able to understand what and how I created a specific model. And this is, we think about it as kind of okay, this should not be very complicated, but when we have a lot of moving parts, things like the code version, the data version, and the parameters, it becomes quite challenging. And again, we don't want to manually have to write everything in a specific, let's think like an Excel sheet or any other way to manually add all those information or all that information so we can later query it. We want that process to be automatic, right? What I have now, I want someone to log it automatically, and then I want to modify it. And then obviously, what is the benefit of this entire process for me as a developer, right? So at the end, there has to be value for me. And I think that the greatest value is to be able to reuse our code in a way that allows us to skip over all the complexities of the DevOps part, right? So the idea is that I, as a developer, I never need to know how to package a Docker and how to spin a machine and how to get my data. There is an entire abstraction layer for me that does that. And that includes reproducing the environment that I'm working on. And that this is an essential, because without it, most of the time I'll be spending on basically logging my environment and trying to reproduce in another machine, right? So that's kind of the goal here. Okay, so the outline for this session is basically how do we use MLOps as developers as part of the R&D process? And then the second part is, so what is exactly resource management, which I'll demonstrate with a very simple scenario where I want to manually getting access to a GPU machine, but then we'll reuse that same process and we'll automate a job for us that will essentially do the same. And then the last one is we'll use the NVIDIA Clara, which is, think of it as a transfer learning toolkit only for medical modalities and scenarios that NVIDIA developed and is part of the ClearMap platform. So basically built into the platform, you log in, you have the Clara examples, and we'll use that as a way to demonstrate how you can build your own MLOps pipeline on top of it, essentially reusing the NVIDIA Clara in order to train our own model on our own set of data, achieving that state-of-the-art, image segmentation, I think. Anyhow. Okay. Bit more about the MLOps in our daily routine. So what is exactly MLOps when you think about the development process itself? So it's always about balance between logging everything and making sure that we have an interface for all the parameters that we introduce into our code, because we always have more and more parameters as we expand and create more complex models on the one hand, and on the other hand, creating an interface that allows us to extend those capabilities without the need to change our base code. The assumption here is that, first of all, our code is constantly changing, and we have to have the ability to take off-the-shelf code base and adjust it, which means that if we have an infrastructure that we need to integrate with, it will really have an impact on our ability to test new models and repositories off of GitHub, because at the end, this is where we all start, right? And if we have an infrastructure that needs a lot of code in order to basically import those repositories into our system, it means that we cannot use them, and that's always challenging. So, and the second is, so what is exactly the criteria for success here? So let's assume that we are trying to implement that MLOps approach. What is the criteria that we succeed in? And the criteria is basically every time that I write code, I have another machine that is training a model for me. If I have that, that means that basically I have full automation. That means that I can start to do things in parallel, right? Because the traditional way is always I'm running it on my machine, which means I'm in charge of training a model, which means I have to be the one pressing the kind of the enter key and starting the training session, and I have to manually monitor my process. So, for example, if we think about Jupyter notebooks, right? If I log into a Jupyter notebook that is running on a remote machine, and I write my code, and I, at the end of the day, run my cell that actually does the training itself, that means that I'm manually executing the code. That means that if my session dies, my model dies with it. That means that I have to log into that machine. And that means that if tomorrow I want to rerun that same experiment, I have to open another machine, manually log into it, take my Jupyter notebook, run all the cells, and monitor this entire thing. If I do that, that means that I'm manually running every experiment. And that's very hard to run several in parallel because you end up with lots of Jupyter notebooks that you have to monitor. That's bad. So if we are at a stage where we have the code that we're working on, whether this is Jupyter Notebook, PyCharm, VS Code, whatever, but at the same time, we have another machine training our code, maybe a previous version, maybe that same version with different data or a different set of parameters, that means we achieved that MLOps goal of automating our process. That means that we are not spending time on packaging, we are spending time in evolving our code base and testing it with different configurations. That's where we're aiming at here today. Okay, so how do we actually get there? And this is a bit about how we think about jobs, orchestration, and kind of the entire approach itself. Okay, so let's take a step back. When we write the code itself, at the end, let's assume that we have some machine with an environment that we worked very hard to set up, and it's working for us, and that's great. We write our code on that machine, and maybe we have some toy data set on that specific machine, or a subset of the data set in order to make sure that everything is working. And on that specific machine, we are able to run our code, test that everything is working, and see some results. That's great. When we get to that step, we essentially built a job template, because at the end, on that specific machine, we have a full setup that is working. We have the data itself, even if it's a partial set of the data, this is still the data. We have the configuration, and we know it's not crashing and somehow converged into a model. Even if it might fail on the real data, we have a job template here. So our goal is to actually take that job template and rerun it on maybe a stronger machine with maybe more cores or more GPU on the full set of data set, and make sure that it actually converges over there. And moving from one to the other, that's the actual challenge. But it's important to understand that once we have it, like, the first step is actually everything that we need. So we all have the information there, right? We have the setup. We can do like pip freeze and get all the list of packages, and we know what CUDA version we're using, or if we're using a CPU version. We have all the information. Now the question is, how do we package that information and create a job template and then obviously orchestrate it? So the traditional way is basically try to create a Docker for everything. But this is very bad. First of all, you end up with thousands of Dockers very quickly. Secondly, they're quite large and it's very hard to manage. There is a better way. And I'll try to explain how that better way is actually working later on in this session. So once we have that job template, we have to think, so how do we use that job template? So let's assume that we can launch it once. How do we automate this process? And the automation of the process is essentially saying, okay, so this job template, I kind of neglected the fact that I had to somehow collect the data, right, for the job to actually train, right? So I have a data collection part, and then maybe I have the data pre-processing, because again, neglected to mention, I did some cleaning of the data, and I have some code that is running. So that's another job template as well. Right, so at the end, we have maybe 3 steps before or as part of the training session itself that we want to run after the other, because at the end we need the model itself, and hopefully the model itself can be deployed. But we have a pipeline of those 3 steps. So a pipeline, we can think of it as a very straightforward DAG, right? It's just a graph with nodes and process one after the other, etc. In theory, that's terrific. In practice, we actually want to have logic built into this graph itself, right? So, for example, if I do some pre-processing and I decide that I don't have enough data, or the data changed and I want to flag it, so there's no need to train the model because the data structure changed, so I want to start the pipeline itself. Another example is maybe I'm running my data collection part, and I realize I don't have any new data. So why would I retrain the model if I don't have more data, right? So that part of the logic, we have to make sure that we can build into the DAG itself, right? So it's not a very straightforward 1, 2, 3 DAG. It should have the ability to introduce logic into it, because at the end, this is what we do. We want to have the automation solved for us, but still have the ability to have full control over the process, which usually amounts to introducing some logic into the pipeline itself. Specifically, let me just demonstrate like an entire pipeline that one of our customers developed. The company name is Theater, and what they do is mostly medical analysis of videos coming from surgery. They build an entire pipeline that constantly takes videos coming in from the operating room, they're analyzing the videos themselves, creating a new structure of the data, right? So think of it as feature extractions from the videos. Those feature extractions are stored somewhere, and then they have multiple models running on those features extracted from the videos, classifying different objects in the videos, different steps, etc. The idea here is they built an entire pipeline that includes a lot of logic on what are the next steps to process. So their process is entirely automatic, which means videos are uploaded to an object storage. Then the pipeline constantly checks for changes in the object storage itself. Then once new or enough data has been uploaded, then it will just reprocess the new data, create a new set of data sets. So think of it as kind of a delta-based feature store, storing the entire features created on the new videos, and then triggering the training of the models themselves. That entire pipeline is built on top of ClearML using all the different modules of ClearML, which are the pipelines and the orchestration and the feature store, etc. The idea here is that they were able to move from writing code on single machines to full automation. And the nice part is nothing here is hard-coded. Even the code itself, meaning the training itself, is taken automatically from the ClearMap platform based on tags that they put on different experiments. And hopefully I'll be able to show that as well. So the idea is even the automation itself is not hard-coded, right? So you have a tag for best model or the current best process for training a model. Then when we have a new one, we just move that tag to a new experiment, to a new job, and that is automatically used in the next time the pipeline will be running. And we still have the full provenance of the full understanding of everything that happened. Okay, so now let's take a step back with all the automation and think on, so how do we achieve the first goal? How do we get a resource, and how do we automate the simple process of running some code on a machine and replicating that code and automating this code, right? Okay. So at the end, the idea is always as simple as possible. Start simple. So ClearML is built on top of the concept of agents. And that concept of agents is at the heart of what we do here, which means that at the end, we separate the orchestration itself from the agent that is running on the machine that actually does the spinning of the experiment and the job itself, right? And the agent itself can live on any machine that you like. This is as easy as pip install. Well, literally it is pip install. So obviously you can scale to Kubernetes, etc., but you can start very small. You can start with a single machine or a couple of machines, spinning an agent on them, and then using those machines in terms of automation, right? So you don't have to start very at the top where you have full Kubernetes cluster deployed. You can start at the easiest way to set things up, and then obviously grow with your own needs. So a bit about the ClearMap platform. It's open source. We have lots of users from all around the world. The idea here is this is fully tested. This is what we're trying to convey here. This is fully tested. Lots of people are using it in very sophisticated setups, but also on a very simple couple of machines connected to a single cluster. So what is the best case scenario when we think about the development itself? The best case scenario is always I have everything local, right? I have my own GPU, I have my own data, and everything is working for me, and I can write my own code and actually, in theory at least, train an entire model on top of it. But in reality, things are a bit more complicated. So I have my code running on my Jupyter notebook or any IDE, so think PyCharm or VS Code, whatever. I can connect my parameters. I'll get to that later on. Basically, most of the parameters will be automatically logged, but I can always extend it. And then I want to test the code locally, which means I want to run it on my machine so I know that there are no bugs and everything is working and the model converged, etc. But then I want the full training itself to happen on another machine, so my machine is free for me to continuously write the next step of the code or other model, etc. Okay, so what we'll do now is we'll start a Jupyter notebook. We will take some code and we will integrate it with the system. We'll add some parameters and then we'll send it for execution on a remote machine. All right, so with that in mind, let me just switch to another window here. Let me just do that. Okay. Okay, so what we do now is we'll start. We just started the Jupyter notebook. Let me just copy paste some code here. Okay, so we started the code. So as you can see, it's running, and now I have a link to my experiment that was just created on the platform itself. If I click on it, it will open the web UI and can see everything that was logged. So all the console output is automatically logged. If I add some matplotlib output, it will be logged as well. The same goes for TensorBoard. Let me just add a few parameters just so we can see them in the UI itself. And let's assume that everything is working and we're happy with it, right? So we have everything working. We can see the output. Terrific. Now let's go into the experiment management itself so I can see my experiment that was created. Now I can clone this experiment. So think of the cloning process itself as essentially copying the configuration of the job itself, right? And having the ability to edit it. So I clone the experiment. Now everything is editable, so I can edit even the code itself from the UI. I have a list of all the packages that I need. If I miss something or I want to change it, I can. I can specify a specific Docker image to be used. By default, I will not. It will be decided by the agent, by the machine that is running, so it will know what's the best Docker for me. I can also go into the configuration tab and change or modify some of the parameters. So let's do that. That should be fine. Okay, and now we want to send it for execution. So sending it for execution is essentially putting the job itself into an execution queue, which means that think of it as just a list of jobs, and then an agent, a machine, will pull those jobs from the list, and it will just set up the environment, and it will run the job for us. So we'll do that. We'll include the job into one of our execution queues. Now I can switch into the workers and queues tab, so I can see the machine itself that is running and that it's just now running my job. And if I go back into the job itself, I can see everything that is done in real time. So all the console outputs, the logs, everything will be presented in real time. The idea here is once I wrote the original notebook, I don't need the actual notebook itself. First of all, it's stored for me. And secondly, I can modify all the parameters from this UI. And that means that I can later do the same programmatically. So the same thing that we did now with a user interface, we can do programmatically from code, replicating, changing, etc. And this is essentially building a pipeline that will automate everything. You can check out the pull-up session end-to-end pipelines. And that over there, we explain exactly how to achieve that, how to automate these processes from code and how to create those pipelines. So now we can see that the code itself is fully executed, and we can see the outputs, etc. Okay, so now what we just achieved is basically we wrote code, and we were able to run it remotely. Very simple. The only thing that we did is we added the 2 lines of code. Again, if this was not Jupyter Notebook, for example, PyCharm or VS Code, then instead of storing the entire Jupyter notebook, it would just reference the Git repository that you're working on alongside with any uncommitted changes. So you don't even have to commit changes if you're working with PyCharm or VS Code. Everything is taken care of for you guys. Okay, so going back to the presentation, let's see some more. So this was assuming that I have a machine that I can write my code on and I have full access to. Sometimes I don't. Sometimes I actually have to get access to a remote machine in order to run my code. Think, for example, a GPU with a lot of memory that is needed to actually run my deep learning model, even a few steps, right? So sometimes I need to do that. And for that, we created the ClearMap session. Basically, it allows us to connect to a remote machine. The remote machine itself is connected with an agent, so any machine on the cluster will do. We will connect to a machine, we'll spin the Docker with everything that we need on that specific machine. Think of it as the development Docker. So in this example, what I'll be doing is using the NVIDIA PyTorch Docker. And then inside that Docker, it will spin JupyterLab for us, or VS Code, or remote VS Code. And now we will be able to run the same exact scenario only on a remote machine, right? So instead of running the JupyterLab on our machine, we will be running it on a remote machine. So with that in mind, let me just switch again to the console, and let's run the ClearMap session. So what we're doing now is we're setting up a new session on one of the agents. It will connect to that session, and it will spin the JupyterLab for us. So let's give it a few seconds. Yeah, okay, and we're up. So now we have the JupyterLab, again, up and running, not on our machine, but on a remote machine. The connection to that machine is actually done, it's tunneled over SSH. So not only it's encrypted, it's safe. So I can basically tell the machines to open the report. That's quite safe. The SSH is fully encrypted, random password, etc., all taken care by the ClearMap session. I also have remote VS Code on the remote machine. So if I need an entire development environment, something more sophisticated than JupyterLab, I have that ability as well. If you can see now, I'll switch to the VS Code. So now I have full VS Code inside my browser running on the remote machine itself. And from that point onward, that's basically the same. We write the code, we add the task in it, and that's about it. And we obviously can clone and re-execute on another machine. So now let's take that experience and translate it into a more of a real case scenario. So when you first log into ClearMap, you will be able to find in the examples folder a folder named NVIDIA Clara, and it actually contains an entire pipeline already built into the ClearMap, so we can reuse this entire pipeline, end up with a model that does segmentation for us without running a single line of code. And the idea here is not only we will demonstrate how that actually works, but the idea is that we should be able to end up with the same process internally and be able to achieve that same automation on our own code base. Okay, so what do we have here? At the end, this solves the reusability problem, right? So what we want to do as data scientists is create something that is working that other people in the company can use, right? So we will now be those other people, and the NVIDIA Clara guys actually wrote something for us, something that is working, and it's already integrated with the ClearMap, and now we'll be the users of those. So think of us as kind of a business analysis people, right? Reusing the code in order to build their own model that satisfies what they need, right? As long as the model actually achieves what they are looking for, then it's terrific, right? Because the idea that object detection model doesn't actually know what it detects, right? It's all based on the data. So in theory, we should be able to replace one modality with another. In theory, we should be able to replace kind of a person detector with a car detector, but at the end of the day, from the model perspective, it's the same. And usually the most of the challenges are the abstraction layer, right? So abstracting the code and the parameters and the data from one another, so we can replicate this process and change one without basically hurting the other. And this is exactly what we'll do now. Okay, so the first step is obviously, okay, we need to get some data in the system. And this is the ClearMap data. So the ClearMap data is a command line utility that allows us to upload data into the system. The storage itself is either on object storage or on the ClearMap server. More of that later. But now you can think of it as a way to use the NVIDIA Clara not on the data that was provided as a sample code, but on our own data. So let's do that. So we'll now run the ClearMap data command line, uploading new data into the data set itself. So even every data set that we are creating is essentially a task in the system. Why? Because even creating data and pre-processing data is usually tied with actual code, right? So think of a code that is running, fetching data from production, creating like NumPy arrays or Parquet files or whatnot, and uploading those into the platform. So that's essentially, on the one hand, it's code, it's a job, but on the other, it's actually a data set, right? So this is what we do now only manually. We do it from command line. It will upload the data for us. And then once we have the data, then the next step is actually running the code itself and training that code on the data that we just generated. So let's do that. So let's clone the code. I'll switch to the other screen. So let's clone the code. Change the data that it's taking and rerun the training session again in real time on the new data set. So now it's starting to run. So obviously I will not wait until this ends. That might take a while. So I'll just show you guys how this looks like. So we started the training session. As you can see, it's running and it's starting to set up the environment, etc. And this is how it looks as the product of that. So we can see all the graphs and we can see the accuracy, etc. Once we have that, we also have the ability to validate that code. So think like training session with training data, validation. Again, same idea. Let's rerun the model only on blind data set, right? The data set that we did not train our data on. So again, let's clone the experiment, start to run it, and validate the model itself. And at the end, we end up with a model. So the model itself stored on the platform, and now we can spin the NVIDIA Clara Train model serving that will just serve the model for us, again, with a single command line. So now we'll open the command line, the bash shell again, and now we will start the model serving engine that will essentially monitor our project itself at every time we have a new model that we publish. So it means that we know that that model passed through validation and we're happy with it. So we can publish it from the user interface itself. And this service will automatically pull it and serve it on the NVIDIA Clara Train. So let's just run that. And yeah, with that, it's done. Essentially, we now have a new endpoint with a new model name, and that endpoint will automatically update when we have a new model published on that same project. So we don't have to touch it again. So that's kind of the nice thing about this MLOps approach, is that everything is automated for us. So we have a central hub that controls all the information, and every process can pull that information from it. So this serving utility, so this Train serving process is actually polling on the system itself, making sure that it has and it serves the latest and greatest model. And then we are free to retrain our models on a totally different machine without worrying. And so how do we deploy it? We don't have to. We literally just say, yay, just publish a model and it's up and running. It is that simple. So if you want to follow up on how to automate this process and how to build those pipelines from code, so we can have 1, 2, 3, basically, instead of clicking through the UI and sending jobs for execution, how do we build those pipelines? Follow up on our end-to-end pipeline session. Essentially, everything that we covered here today, only more hands-on and kind of the code that actually replicates everything and builds those more sophisticated pipelines. A few takeaways. The idea is always spend as little time as possible on integration. This is why the ClearML was designed and with that in mind. And it's literally only 2 lines of code that you have to add to your code base. It's the import of the package and the initialization. That's it. Then the second step is always start small when it comes to orchestration. Start with only a few machines and then grow from there. ClearML will support you with any combination that you'd like. So either on-prem, on the cloud, DGXs and Kubernetes with any combination that you like. Hopefully we'll have a more on that later on. If not, check our website. We have documentation for everything. And hopefully we'll see you dip your toes into the MLOps pool quite soon. So a few links. Go to the GitHub, star us, look for us on the ClearML Slack channel, or send some questions on Stack Overflow. We are almost always there. Thank you guys so much. Hope you enjoyed it. Bye.